Good evening, welcome to the week 7. This is the homework portal, or what we call it as the newly framed name as the one problem per day. So today we are going to start with the new chapter. As we already know that we have started with electricity for IB1 students, and for IB2 students it's a revision classes going on. So as a result of it, I thought maybe we can have something on atomic physics, nuclear physics and quantum physics. So this will be the theme of the week. Every week we will take up one theme. Like for example, we will take up 1 week as electricity, 1 week as data analysis, 1 week as quantum mechanics, and so on, so that we will be able to revise everything. Initially I thought of doing it randomly, but now I thought, okay, let me do something like this. Okay, so I not put the timer over here. Let us start this, because what I observe is, okay, we are not able to go along with the timer. Someone also commented on this saying that, what is the use of putting the timer? I thought maybe it will be useful by considering something like how much time we are taking to solve a problem. Generally in structured problems we are solving it appropriately, but MCQs is taking a delayed time. But anyway, let me see how does it work for this particular problem, because there's one more psychological thing that's happening, that in the event of solving a problem within a stipulated time, okay, I also try to rush sometimes. So I thought, okay, why do we need to do it? Because the primary aim here is to solve it, okay, with making an understanding, making it to see to it that you people understand it, okay. But if I rush through it, okay, then there's no point in solving and putting it across in YouTube. Okay, now let us begin with this. Right, so resistor R is connected in the circuit. This is for the IB1 students. Today 13th, this is of 14th. Let me write it down. This is for the 14th of October 2024. Okay, now resistor R is connected in the circuit. The cell that has internal resistance over here. The ammeter and the voltmeter are ideal. Ammeter and the voltmeter are ideal. Okay, what is meant by an ideal voltmeter? What do you mean by ideal voltmeter? Ideal voltmeter means the resistance of the voltmeter is infinite. Okay, maybe if they had asked you about what is an ideal ammeter, then what will you say? The resistance of an ideal ammeter would be 0. They can ask you like this also. There's one more way of writing this here. When you say the resistance of the voltmeter is infinite, that means no current passes through the voltmeter, which means what? See, any current that is being given by the battery, it comes all the way along, passes through the ammeter and the resistance. It does not pass through this one, because it acts like an open circuit, right? In an open circuit, do you have any current passing through? It will not pass any current. No current passes through it. So therefore, this is the answer for it. Next question. The resistance of R is 50 ohms. The voltmeter reads 1.47 volt. Calculate in milliampere the current in the resistor. The resistance of R is 50 ohms. This is 50 ohms, and the current, what is the value of the current? 1.47 amperes. 1.47 amperes. And as a result of this, what is the current in the resistor? Now how do I find the current over here? 1.47 volt. I'm sorry, I made a mistake here. This is ammeter. I should write this as the voltmeter here. This is 1.47 volt over here. So what is the current? The current here is nothing but, see, if this voltage is known and this resistance is known, and this is also an ideal ammeter, which means what? This has a resistance equal to 0. Whatever voltage is here, the same voltage is drop across this resistance, which means I can find out the current by using the formula 1.47 divided by 50 ohms. What did I do? I just put V by R, which is equal to I, which means I use Ohm's law. Okay, so therefore the value here is 1.47 divided by 50, which will be equal to, let us find out, use my calculator. 1.47 divided by 50 will be 0.0294 amperes. So the current I is equal to 0.0294 amperes. I want to write it in milliamperes. It should be 29.4 milliamperes. Okay, then next question. Resistor R is replaced by another of resistance 10 ohm. The ammeter now reads at 139 milliamperes. So what are we doing? We are replacing this one. We are replacing this one with a 10 ohm resistor. We are going to cut this off. Okay. and as a result of it, the current now reads 139 milliamperes. 139. See, earlier what was the current passing through it? The current that was passing through, we found out this as 29.4. 29.4 milliamperes was the current here. But when you reduce the resistance, what will happen to the current here? Current will be more, right? Are we finding this in the question? Of course, we are finding this. This is 139 milliamperes. Show that the internal resistance of the cell is about 0.7 ohms. Show that the internal resistance of the cell, which means what is the resistance here? Okay. Now we need to do this. So what do we know? Now let me write down here. The new resistance, new current is 139 milliampere. The new resistance is 10 ohm, and then we need to find out this. Then what is the voltage over here? Is the voltage given? Voltage was 1.47. Anyway, this EMF is not known to us. Okay. Now what we do is, let us start applying the Kirchhoff's voltage law for this particular loop, for this loop. So first what we do is, let us consider this condition, because you know, when I change any one of these parameters, when I change this value of resistance, this R is not going to change, this E is not going to change. Okay. So therefore, let me arrive at one equation. I will collect some data and then I will proceed further. So when I am doing this, then what will happen? Now a current I flows like this, ideal voltmeter, no current passes here. Now what was the earlier current? Earlier current was 29.4 milliampere. So I will write 29.4 milliampere multiplied by R, right? This current comes here, multiplied by earlier resistance of 50, and then it comes over here, Now this resistance is R plus R, okay, is equal to what? Is equal to this E, okay, is equal to the EMF of the cell. We have written this for the first condition. The second condition, what is the second condition? Second condition, I replace this by 10. So this is 139 milliampere. Now I will write the same thing, 139 milliampere multiplied by, what is the new resistance here? 10 ohms plus, what is the old resistance here? New resistance here. This has not changed. Plus R is equal to EMF E. Okay, sum of the IR drops equal to total EMF. I use this one. So 1 and 2 are same. So I can equate one with the other. So I will get this as 29.4 into 50 plus R is equal to 139 into 10 plus R. When I do this, now it's easy for me to solve. I'll get different values. So let me expand this. I'll get 29.4 into 50 minus 139 into 10. I'll send the R terms that side. Okay, which should now be equal to, what is that we have? We have 139 into R, 139 into R minus this one 29.4 times R. I get this value. Now let me simplify this value. Okay, now what is this? I get over here, this one is, take the calculator here. Now 29.4 star 10 star 50, star 50 is equal to 1470. I will write this as 1470 minus 139 into 10 is 1390 is equal to this one 139 R minus 29.4 R. What is it? 139 R minus 29.4 R is equal to 1096 per R. 109.6 times R. I get this value here. Then what do we have here? Am I missing something? No, I'm not missing anything. Everything is correct, right? Okay. Now what do we have here? So let us subtract this. 1470 minus 1390 would be, here 10, there is 70, it is 80 here, is equal to 109.6 times R, which means R should be 80 divided by 109.6. What is this value? Let us calculate that also. So I get this as 80 divided by 109.6. I get this as 0.7299. Okay, it is 0.73 ohms. Thus the resistance R is equal to 0.73 ohms. Resistance R equal to 0.73 ohms, and this asked about 0.7, so closer to 0.7 ohms. Okay, I hope you understand this. If not, if you did not understand this, that means you have not understood the Kirchhoff's voltage law application. Ask me once again, put this in the comments. I will definitely take up some 3-4 examples to illustrate how to apply Kirchhoff's voltage laws. Okay, now let us move on to the next one. Calculate the EMF of the cell. What is the EMF? Now let me go back to the circuit. Now the circuit, where is the EMF? EMF is here. EMF is here. This is your EMF. Now we know that there is a rule, okay, connected to a potential difference, terminal potential difference. What is that? Terminal potential difference V is equal to E minus IR, right? So therefore, your EMF is equal to V plus IR, correct? Now what is V? V was, what is it V? We already taken V equal to 1.47. When did we take this? When the current was 29.4 milliampere and your resistance was, and your what is this R here? This R here we already found 0.7 ohms, right? So let me write it down once again here. That is it. We know that E is equal to V plus IR, which should be 1.47 plus current was 29.4 milliamperes multiplied by 0.7. Just now we found out here, right? The internal resistance is going to be 0.73. I got 0.73. 0.73. When I do this, what is it I get once again? Let me take this value, keep it here. So it should be 29.4 into 1 into 0.73. 0.73. I get the answer as 21.462. I'll write this as 1.47 plus, what is the answer I got? 21.462. 21.462 millivolts over here, because you have milli here, right? So you need to write this one. So which should be 1.47 plus. Now let me convert this into the proper voltage over here, because there is no milli here, right? So I will write this as a 0.021462 into volt over here, which should now be equal to, now let me cancel this. I will write 1.47 plus 0.021 will be 1.491. 1.49 volt over here. Okay, and if I consider only two significant figures, this would be equal to 1.5 volt. Okay, now let us move on to the next one. One of the connecting wires is placed in a magnetic field. Okay, there is a current which is going, there is kept in an external magnetic field now, right? The direction of the current in the wire is shown. Okay, this is your direction of the current. Explain with reference to charge carriers in the wire how the magnetic force on the wire arises. Why do we get a magnetic force when a current carrying conductor is kept in an external magnetic field? Okay, this is an obvious fact, everyone know, but we need to explain here. So why do we get this over here? Okay, let me explain. So what happens when the current is now passing like this? What is the magnetic field over here? Keep your right hand rule. Now you see the magnetic field goes downwards below the wire and comes outwards above the wire. See, this is my current over here. The pen that you see is a current over here. So therefore it goes, if I keep it here, so it goes below like this and comes outward like that, right? So therefore it goes below like this and comes outward over here. How do you write below? Below is written like this, outward is written like this over here. Okay, so the first point, see how many marks is this now? This for 2 marks. So what you should write? The first one is movement of charge carriers, that is current produces a magnetic field. This will give you 1 mark. Then secondly, now what does this magnetic field do? This magnetic field interacts with the external magnetic field to produce a magnetic force, right? Second one, we have got both of them. Next, let us move on to the next one. Identify the direction of the magnetic force on the wire. So which one will you use? So use FBI rule, or maybe you have to write something like Fleming's left hand rule, but writing this will not give you a mark. Okay, you need to mention how do you use this. So what do you do here? Use your FBI over here. Let me go back to the figure. So FBI, first what I will do, I have to write down what is the direction of the magnetic field, and then I need to find out what is the current passing through it. Now let us assume this one over here, FBI. Okay, so now what is this magnetic field here? This is your magnetic field. Okay, don't take this magnetic field. The magnetic field produced by the current carrying conductor is not required. We should take the external magnetic field. Okay, so magnetic field starts from north and goes to south. Now this is the magnetic field. So what will you do? Align first the index finger. So where is it? Now index finger on the left hand side. Not use the right hand. Okay, this is my right hand. This is my left hand. Okay, So therefore this is your BO here, and current, what is the current over here? Current is now like this over here. Now what is the force? Force is into the page over here, right? So force is into the page. So you should just write the magnetic force. Force is into the page. Into the page. That's it. This will give you 1 mark. Right. Okay, so with this we come to an end to this problem. Let us see the next problem in the next video. Thank you.